Hey guys, today we are going to revise our chapter number 5, which is integrals. So we will technically divide it into two parts. First one would be for addressing the topics that we have covered in our chapter number 5, and secondly we will see some examples and exercise questions. Actually you have to solve them, and I'll see whether we have built some sort of understanding for this chapter or not. Right, so without any further ado, let's move there. Okay, first one we have antiderivative. An antiderivative is actually the inverse of a derivative, or can say finding antiderivative is the reverse of finding derivative, right? So by definition it says a function capital F is called an antiderivative of small f on an interval I if capital F prime of x is equal to f of x, or we can say the derivative of capital F of x is equal to f of x for all x in I. It means that the inverse of this particular derivative is our antiderivative, right? Now have a look on this theorem. It says if capital F is an antiderivative of small f on interval I, then the most general antiderivative of f on I is f of x plus c, right? And c is actually the arbitrary constant. So it seems like the actual or the general form of our antiderivative is f of x plus c. Okay, next is we have different formulas over here in the table of integration formulas, and we know that these are really helpful to solve different problems of integration, right? So we have different formulas like power rule formula, logarithmic rule formula, and different formulas of trigonometry. So we just omitted the constants because we know that it's understood whenever we solve the integration there would be a constant alongside with particular solution, right? So we have omitted those constants from integral. We have two kinds of integrals actually. First one is definite integral and second one is indefinite integral. So in definite integral we have the upper and lower limit for our integration, right? There is upper and lower limit given in particular expression, but when we talk about the indefinite integral it's free of limits. We don't have upper and lower limits, right? So here we can see that we can see over here it's integration a to b. It means that this is the definite integral because it doesn't it is having the upper and lower limit, right? Here this is the lower limit and this one is the upper limit, so we can say this is the definite integral. Now we have this definition for definite integral and we will divide it into two parts. First part says that we have a particular function and we will divide that particular function into the subintervals, right? Suppose we have a function and it has interval a to b, and what we do, we divide it into different subintervals, right? And then we will find the delta x, which is actually one subinterval or the width of one subinterval. And we know that how we find the delta x, it's b minus a divided by n, right? So this is how we find the delta x. After that we will be assuming x naught equal to a and x1 x2 x3 up to xn equal to b, right? These will be the endpoints of these subintervals, and we let x1 x2 up to xn to any sample points, right? And then we will be defining our, so what do? Actually we'll just find the width of one particular subinterval, then we will add all those subintervals and we'll find the area under that particular curve, right? So you can see over here we have this formula for definite integrals, right? It says integral a to b f of x into dx, right? And it would be equal to limit where n approaches to infinity sigma f of x I, where I is equal to 1 and goes to n into delta x. So this is actually how we find the definite integral, and we solve a particular problem of definite integral, right? And it says additionally, it says that if it does not exist, we say that f is integrable on a to b, right? Okay guys, now we have the properties of definite integral. And when we define the definite integral a to b f of x into dx, right, we implicitly assume that our a is less than b, right? But we have this particular property, right, which is different than our assumption over here. So you can see definite integral a to b f of x into dx is equal to, sorry, that is definite integral b to a f of x into dx equals to minus integral a to b f of x into dx, right? So what happens here, we have, you can see that when we interchange the limits, when we interchange that upper limit with the lower limit, we got this negative sign over here. So we will multiply by this negative sign, right? So we are actually multiplying it, this function, with our negative sign, since we interchanged our upper limit with our lower limit, right? We brought this b over here up and a down over here. So now we will having our this negative sign. So that's one property, understand? Right, now we have the second property, which is integral a to a f of x dx is equal to 0. Now it means that when we have this a, it's constant, right? So this constant will be 1, 2 or 3, and this constant is actually on the lower limit as well as at the upper limit, right? So this answer would be 0, because we know that it will be subtracting over here, so it will be equal to 0, right? Then we have another property, which is integral a to b c into dx, and c is actually our constant. It could be any constant. So it says that this expression would be equal to c into b minus a, which are the constants of any limit, constants of our limit. All right, now there is another limit, another property of our particular integral, which is integral a to b f of x plus g of x into dx is equal to integral a to b f of x dx plus integral a to b g of x dx. Now this could be called as additive property of our integral, right? Then there is another property, which is integral a to b c multiplied by f of x into dx is equal to c integral a to b f of x dx. So what happens, we are having this constant over here, right? So we just take this constant out of this integration, right? And it would be on the left side of our integration sign. All right, the next one is integration a to b f of x minus g of x into dx, right? It's equal to integration a to b f of x dx minus integration a to b g of x into dx, right? So it means that we are just simply subtracting over here these two functions. We have these functions, and we can just write down in this particular form as well, right? Now we have this particular last property, and this is really interesting property. In this property, it says integration a to c f of x dx plus integration b to c to b f of x dx is equal to integration a to b f of x dx. Well, now what happens, actually we have a particular area, right? And in that area, what do? We divide that area into two parts. First part is from a to c, and second part is from c to b, right? So suppose this is the first part, this is the second. So we can just, we can add this area into this area, and it would be equal to the total area we have, understand? So do not confuse yourself. All right, guys, so getting done with these properties, we head towards the fundamental theorem of calculus. And this is really important theorem because, fundamental theorem is the one which relates derivative to integration or integrals, right? And reason why it is called fundamental theorem, because it involves the derivative and integration both. And our first half of the calculus is all about derivatives, and second half is all about the integration. So these two major concepts are covered by this. So we have two parts for this fundamental theorem of calculus. In the first part, it says if our f is continuous, right, if there's a function f continuous on AB, then the function g defined by, sorry guys, so it says if f is a continuous on AB, f is a function which is continuous on AB, then there's a function g defined by g of x is equal to integration a to x f of t into dt, right? So what happens when we take the derivatives, and it says it should be continuous, it should be differentiable, right? And when we take the derivative of this g of x, it would be equal to f of x. So what do we have here in this particular integration? We have one variable over here, right? We have the constant and we have variable, right? So when we have this variable over here and a constant over here, and when we take the derivative of this particular thing, and it becomes f of x, this equation will be equal to f of x, right? So that's actually the fundamental theorem of calculus. Now, using the Leibniz notation of derivatives, we can write this theorem as d by dx integration a to x f of t into dt is equal to f of x, right? So we can just change this g prime of x, right, with d of x. As we know that in Leibniz notation, we can just write d by dx, right? Calculus, we have some other conditions as well. Suppose if we have the lower limit as a and upper limit as b of x, which is a function. So if we have a our lower limit is constant and upper limit is function, we will be expecting it is equal to f of b of x into derivative of b of x, right, or b prime of x. And in the second one, we have the upper limit is b, which is constant, and lower limit is a of x, which is a function. We will be having minus f of a of x into a derivative of x, right? And in the third one, we have the upper limit is ax and the lower limit is ax, and upper limit is bx. So we will be having f of b of x into b prime of x minus f of a of x into a prime of x. So these are the three conditions. Like when we have our upper limit and lower limits changed, right? So instead of the constants, the regular constants, if we have functions or the variables, it will be changing. The consequences or the answer would be changing, or like. So in the second part of the fundamental theorem, it says integration a to b f of x into dx is equal to f into b minus f into a, which means that it is like we have to solve this theorem, and when we'll solve this particular integration, right, our answer would be in the form of f into b minus f into a. We have to multiply our function with the integration of the function with b and with a, and then we have to find the difference of this particular solution, right? So where f is an antiderivative, right, this is a function such as f prime of x is equal to f, right? So this is all about our second part, which is very simple. In the second part, it says we have to find the difference of our antiderivative multiplied with our upper and lower limits. Next is strategy for integration. So first of all, we have to simplify the integrand if it is possible, right? If it is not possible, then we can try something else. But if it is possible, we have to give it a try by using algebraic methodologies or trigonometric identities. We can simplify the integrand, right? And we can make the method of integration obvious. So you can see we have some examples over here, and in the first example we have integration under root x into 1 plus under root x, right? So we just simply multiply these two and we write it down in form into under root x plus x, right? Similarly, we have these examples, right? Tan theta by secant square theta into d theta, right? And we just try to simplify it as well with the help of trigonometric identities. In this example, you can see we have to simplify this integrand, and our integrand is sine x plus cos x square, right? So we will simplify it algebraically, and by simplification we have to solve the square over here, and when we solve it down, it would be equal to integral 1 plus 2 sine x cos x into dx, right? So this is actually the first thing you have to attempt. You have to simplify your integrand if it is. Second thing is look for the obvious substitution. So you try to find some function u is equal to g of x in integrand whose differential du is equal to g prime of x dx also occurs apart from the constant factor, right? For example, if we have this particular expression over here, integral x by x square minus 1 into dx, right? Now we just substitute it with u is equal to x square minus 1, then du is equal to 2x into dx, right? Therefore we use the substitution x is equal to u is equal to x square minus 1 instead of the method of partial fractions. Third is classify the integrand according to its form. So if you think that step 1 and step 2 are not helping out to lead towards a solution, you can just have a look on your integrand, which is f of x, right? So if it's trigonometric functions, you can just treat it accordingly, right? Or rational functions, if f is a rational function, you can use the procedure involving partial functions. Then again, for integration by parts and radicals, right? So you can just try, you can have a look on your integrand and you can treat it accordingly. And finally, it's number 4, try again. If first 3 steps have not produced the answer, remember there are basically only 2 methods, which are substitution and by parts. So you can try substitution or try by parts, although integration by parts is used most of the time on products of the form described in step 3c. Relate the problem to obvious problems. When you have built up some experience in integration, you may be able to use a method on a given integral that is similar to a method you have already used on a previous integral. Alright, number E is use several methods. Sometimes 2 or 3 methods are required to evaluate an integral. Evaluation could involve several successive substitutions of different types, or it might combine integrations by parts with one more substitution, right? So guys, that was all about the strategies of integration, right? So now we have these typical examples. You have to solve these particular questions in order to let me know your understanding about integration, right? These are not really typical, or these are not really difficult. These are typical integration questions. You can just solve them. There are 4 questions. In fact, you can solve them and you can just send me out later in the WeChat. Thank you so much for today, and I hope you'll be clearing up with the questions as well. And if you have any problem, then we can just discuss it in the question and answer session.